So now all this, now I need to define what is a so this is about topological space and the map of topological space, spectrum. Now just like in variety, you see that a same topological space may have different variety structure. That as a topological space they are homeomorphic. Two variety, we have seen examples, right? Many examples, right? The topological spaces are homeomorphic does not mean, for example, what is the example of homeomorphism which was not isomorphism? T going to T to the power P, something like that, right? A1 to A1. You take a T, you send it to T power P, A1K, say, over the field. This map was not, because the finite, if it is a isomorphism, then the coordinate ring has to be isomorphic because they are one-to-one corresponding. But one part you see a key, it is one k x power p, which is a subring of kx, which they are not isomorphic, right? Similarly, here two schemes are isomorphic. Just topological space isomorphism should not be the. I mean, you don't expect that to be isomorphism of scheme, affine scheme. So you have the functions will play an important role. So how do you define functions? So we already saw that if I take an element here AF, then this AF defines a function on spec A. But this function only it is peculiar because it does not take value in a single field, it takes value in the different field. But this kx is the residue field. This is little peculiar. So model on this, we want to define functions. I want to define some sheaf on OX, say X is spec A. I want to define a sheaf structure on spec A. So that means for every open subset U, I want to define some ring or some object OXU, which should have some sheaf property. Right? No, that is not the true. Recall in the variety case, when X was affine variety, how did you define your OXU? Affine variety. Locally OX of U. So OX of U is regular functions. So how do you define regular functions? For every X in U, it's not that it is of the form f by g, but f and g are polynomials. No. For every point in U, there is some neighborhood V containing X and which is inside U, such that when you take this the AF restricted to V is of the form. It was not globally there. The function f need not be globally defined, like in the case of variety. I mean, when it was not affine, any variety, sorry. In the case of variety. In the, for example, projective space, there are no functions, global functions, but they are local functions. Right. So similarly, here you should not expect that it is just of the form f or f by g, where f and g are element of A1. But locally they should look like that. So OXU, so these are called sections. In the case of schemes, affine schemes, the functions are called sections. S from U to disjoint union of Kx, x belongs to U, such that for every x in U, there exists a neighborhood Vx containing x and inside U, such that S of y is equal to f by g, where g does not belongs to y, for all y belongs to Vx. So this is the way of defining functions. So what does it say? These are all the maps. You can think these are set of maps U to this. For every point in U, you get a neighborhood around that point, such that this function looks like f by g. Of course, to define g of y should not be 0, but g of y should not be 0 is same as saying that g does not belongs to y, the py. See, to define s of y equal to f by g, g should not vanish on y. But g should not vanish on y is same as saying that g should not belong to the prime ideal y. F and G are elements in your A. See, element of A you can think as a function on spec of A. But now S of Y, it is should not so A, I mean it's not S of Y, I mean S looks like S restricted to V of Y or V of X is F by G. That means S of Y is equal to Fy by Gy, and Gy should not vanish. But Gy does not vanish means G does not belongs to Y. On Vx. So when you restrict a function as it's a function from U to V for every point X around that. The only thing is that you have to be a little careful that the function does not take value in a single field. And now you can define sum of two sections S1 and S2, S1 plus S2, S1, S2. So this is a ring. For every U, you are defining a ring. Natural sum and natural multiplication. Because after all, the range space is a field. It has a multiplication. It has an addition. Because S1 and S2, if you take two sections, they are taking for every point X, you are going to the same field. So now this is the sheaf, and this forms a sheaf. You have to check that this is a sheaf, that OX is a sheaf. On X. Yes. This AX with this sheaf structure, this OX is called structure sheaf. Because from A you got it, right? See, I did not give you anything else. From A I got it, I am getting everything. So that's why it's called structure sheaf. That means it's embedded, it's inherited, the sheaf structure. Just like regular functions, when you had a variety X, the sheaf structure was automatic. When you have a variety, you are given a affine variety, you get the sheaf structure naturally through polynomial function. So here also you are getting the structure, this sheaf structure automatically from A. So that's why it's called structure sheaf. So the upshot is what? That you start with a ring A, you not only get a topological space, you get a topological space along with a sheaf of functions or structure sheaf. And this XOX is called affine scheme. sometimes this is called spectrum of a ring along with this structure sheaf. When a spectrum of a ring is not just spec of A, it is also the structure sheaf associated to that. This is called sometimes spectrum of A. The ring associated with a topology. So, every ring associated with a topological space and a sheaf. So, now once you have a sheaf, you can talk about the stock at a point, right? Stock at a point, and what about the suppose X is spec A. So, the functions on DF, the basic open subsets. DF is an open subset. So, what is the OX of DF? It is AF, localization of F at A. F is a element in A, OS, so this is one. And what about if you take a stock at a point? So, whenever you have a sheaf, you can talk about stock at a point, AP, localization at the prime ideal P. And what about so DF, if you take the whole space X, that means OX of X. Sometimes this is denoted as the global functions, that all the functions on the whole space X. So, this is nothing but A when X equal to spec A. So, these are all you can check. And then I just want to define what is called a scheme in general. So, so I need to define what are called locally ring space. So, first of all, a ring space is a topological space with some sheaf, say OX. So, say OX is a sheaf of rings. Sheaf of rings, and X is a topological space. So, then this is called a ring space. And morphism between ring space is if you have a map from AX OX to Y OY. Morphism between two ring space is a map F and F hash, where F is a map from X to Y and F hash is the map from OY to F lower star of OX. Whenever you have a map of topological space, you can push forward the usual definition. Now, so now this is a ring space, so XOX. Now you call XOX is a locally ring space, is called locally ring space. So a ring space is a topological space with a sheaf, right? Sheaf of rings. Now locally ring space, if you take the stock of OX at a point P, this is a local ring. OXP is a local ring for every P belongs to X. So, in particular, when you take, for example, X, if you take XOX to be the spec A and the structure sheaf of spec A. This is an example of a locally ringed space. Because what is the stock of the structure sheaf at the point P? O of spec A at a point P is nothing but A of P, which is a local ring. So it is a locally ringed space. And now, if you have a two locally ringed space, suppose XOX is a locally ringed space, YOY is a locally ringed space. Both are locally ringed. Both are locally. So now I need to define what is a morphism. I define morphism of ringed space, but morphism of locally ringed space should be more specific, right? Yeah. So this is, it should take, so this is morphism. So morphism between locally ringed space is a morphism of ringed space So this, you have this map, right? OY to F lower star of OX. Now you have the point OY of FP. So this will induce a map of OY of FP to OX of P. At the level of stock, whenever you have a map, now this map, it should take the maximum. So OIFP is a local ring because it's a locally ringed space. This is your F hash, and this F hash P, the stock at that point. Now this should take the maximal ideal of FP to the maximal ideal of P. So it's called local homomorphism. It is a morphism of locally ringed space. So now a scheme, what is a scheme? A scheme is a locally ringed space which is locally looks like spec A. So if I say X is a scheme, XOX is a scheme. If locally it looks like spec A, O of spec A. If locally it looks like so it's a local ringed space, and the model is spec A. That means whenever you have a topological space XOX and you take an open subset UX, then you can restrict to U, right? OX restricted to U is, yes. UOX restricted to U is isomorphic to spec of A, O of spec. So if you see definition of manifold, what is the definition of manifold? Locally it looks like Rn, a differentiable manifold. But the functions also, you have some C infinity function. The C infinity functions are basically functions on Rn. So here also is a locally the functions on your scheme looks like this. So this is the model. I mean, so it's very general, like it's a spec of a ring in some sense. So locally it always looks like spec of a ring with the structure sheaf. So this is the most general definition of scheme. Now you can talk about morphism of schemes. You can all talk about proper, when it is proper, when it is closed immersion. So all those properties of morphisms. When it is separated, when it is smooth, all these things of definition which you have seen for varieties, everything you can generalize for at the scheme level. Huh? They are covering, yeah. Because for every point you have a neighborhood which looks like this. Locally means that. But but it is very diverse in the sense that you are no longer over a field. You are over any ring, like in particular over Z. And once you do something on Z, that means it's characteristic, mixed characteristic. Every time you localize at some prime idea, you get something over Fp. Right? If X is a scheme over Z, X is a scheme over Z, spec Z. Now you have from Z to Z mod Pz. So there is a map from spec of Z mod Pz. Now you can do the base change. So whatever object you get here, X cross this spec of Z mod Pz, this object is defined over Fp. This is a Fp, finite field. Though this is over spec Z, you can reduce your thing to over a finite field or over characteristic P field. Right? So this kind of flexibility is there, that you can always. So sometime you want to study this kind of questions, that something about finite fields of characteristic P. So you go to the scheme over Z, define something, and then come down to and study here, and then many properties like properness, smoothness, they are invariant under base change. Right. So this is how you make the transition. So that's why scheme theory is when you do arithmetic geometry, number theory related problems, scheme theory is kind of very, very useful. When you do complex geometry, still you can think of variety, and you can still manage to think in terms of variety, but there is no other way of thinking algebraic geometry without scheme theory if you do number theory. That's the point. Okay, I'll stop here with this. I'll stop here.